Hi everyone, this is Professor Fernandez, and in this video we are going to talk about Module 1 of Lesson 13. We are talking here about scalar integrals over planar curves with respect to arc length. So it seems like there's a lot going on, and I wanted to start right off in the lesson notes with this definition. To give you a little motivation for this new lesson and this new topic, I'm going to go back to what you are familiar with from Calculus 1 when we're trying to find the area under the curve. So I've drawn here a function y equals f of x, piece of it, and we're trying to find here the area under the graph of y equals f of x and above the x-axis between x equals a and x equals b. We know, especially from this picture, because f of x is positive, that the area is given by this definite integral. And remember also how we got to that definite integral as a Riemann sum. I won't review that because we've been talking a lot about Riemann sums already, so we've mentioned it in the previous lessons. But the notion is that if I now look at this picture, which is a perfectly okay picture in single variable calculus, and I imagine that instead I'm looking at a function z equals f of x. So I'm basically now adding the a third dimension. It looks a little lonely in terms of what we're calculating here with this area. There's so much room over here that we are just not using. In other words, when we were working just in the plane, life was fine in single variable calculus. There was no third dimension. We had the x and the y axes. Now in multivariable calculus, we have 3 dimensions, and we have all this space to spread out into. So what if, for example, going now to this picture, you are looking at a surface, z equals f of x, y, and you look at a blue curve on that surface. I'll zoom in here. Blue curve on that surface that goes from a point on that surface to another point. And you look at the projection of that blue curve onto the xy plane. So this red curve over here, C. What if I wanted to find the area of the, quote, curtain that is created by this blue curve and its projection onto the xy plane, into this curve C? Right? So this is a more interesting problem than what we were doing up here because it is not the flat version that corresponds to this picture. It is, excuse me, a version of finding the area under the curve, where here the curve is coming from some 2-variable function, and it's not relative to a line segment base like was the case over here and over here, but it's relative to some curvier thing, this curve C. So that makes life a little more interesting. And how would we do that? Well, so first of all, I'll give you the notation. So the area of this curtain we are going to denote by integral f of y ds over c. And that is what we're going to call the line integral over the curve C with respect to arc length. And the definition above walks you through how we obtain that, and I'll just mention a few things about that. What do we do? The definition says you start with the curve in the plane C that you're trying to find the line integral over, and you chop it up into little subcurves. So the subcurve from here to here, the subcurve from here to here, and the subcurve from here to here, and here to there, for example. This partitions the curve into subcurves. And then on each one of these subcurves, you pick a point, and that becomes, for example, your x star 1, y star 1. And then you evaluate that point so that you get a f of x1 star, y1 star. That is this value on the function itself. And then you do what we usually do. So we multiply we create a rectangle basically, and we find the area of that rectangle. In this case, we can take this, let me put it in red, we can take this arc length, and if we call that delta S1, and then we multiply it by this height over here, then we're getting f of x1 star, y1 star, times delta S1. This starts looking kind of like the area of a rectangle. It's not exactly the area of a rectangle because this little delta S1 here is a small curve, it's a little arc. But, we can take this arc and we can kind of stretch it out. And then it would be an honest to goodness rectangle with some height f of x 1 star, y 1 star. So we can think effectively as if we were creating little areas, rectangular areas here, and you can see as I'm drawing them, that they kind of approximate the curtain area, so to speak, which is the actual area under this blue curve all the way down to the red curve. So long story short, that is what's going on in this definition here. I won't go through the entire definition, partly because you've seen this before. We talked about it quite a few times in the double and triple integral context. We are just partitioning a curve now into a bunch of other little curves, and then calling again the norm of the partition, the maximum, in this case, of the lengths of all these small little curves. And then we're adding up these areas that I showed you that come up from this way of approaching the problem, and taking the limit, and then eventually obtaining what we're now calling the line integral. So that's a very excuse me, quick introduction to what's going on. I did put in here a link which I think is really useful, so I'm going to click on this link just to see what a line integral does. And this is to an open source textbook, and I'm going to start describing what is going on in this diagram here. So we see the contour plot of a function f. And then now a curve on the function from a to b is drawn, and that curve is on the function at c. So you can see here as we rotate it's on the function. The projection onto the xy plane is the red curve. And all that blue is this curtain that I've been talking about. We can stretch it out to think of it as we did in single variable calculus. And if we found the area between this top blue curve and the red, that is our line integral. So that's exactly what we're doing. This expression on the right-hand side is another way to get at the line integral that we will talk about later in this lesson. So to view this one more time, excuse me, again, you have the curve C on the function. There it is, it's on the function. The projection of that curve onto the xy plane is the red curve. And then the blue is the curtain that we're finding the area of. Notice that there's some curtain, so to speak, under the red curve. So as in single variable calculus, you don't just get an area. If the function has negative values, you get a net signed area of this curtain. Okay, so that is a good visualization of what a line integral does and yields. So how about calculating line integrals? All right, so I'm going to derive for you how we calculate a line integral using a technique that you should probably recognize from the arc length formula, back from single variable calculus. So here's what we're going to do. First of all, I'm going to say that I'm going to assume that we're dealing with some curve. So I'm going to go back to single variable calculus. Excuse me. And I'm going to assume that this curve goes from some point, let's call it P and Q. And I'm going to assume that this curve C is parametrized as x of t, y of t, where t goes from A to B. And this P is x of A, y of A, and this Q is x of B, y of B. So in other words, the curve starts here and it ends there in terms of the parameter t. And what am I going to do now with it? Well, I'm going to assume, let's say you're here, and this point is x of t1 and y of t1 at some time. And then a little bit later, you move over here, and this point is x of t2, y of t2. So what I'm going to do now is I'm going to pop out this little region over here to make it a little easier to see, and I'm going to work with this change in time and try to extract from it information about how the arc length changes in terms of a change in x and a change in y. So to do that, I'm going to draw a little right triangle here, here, and then I'm going to put the line segment in between here. So the actual change in the arc length, delta s, is this little bit, the red change in the arc length. I have gone a little bit of change in x, that's this much, and I have gone a little bit of change in y, that's this much. So from the Pythagorean theorem, I know that delta s squared is delta x squared plus delta y squared. Now all of this has happened after some change in time, right? I went from time t1, I was here, and then I waited a little bit, time t2, I was here. In other words, I was drawing out the curve in time, and that time I'm thinking about as my parameter t. So what I'm going to do on the right here is I am going to divide this expression by delta t squared, and then I'm going to multiply it by delta t squared so that I don't change the expression. And then I'm going to put in this delta t inside the parentheses here so that I can square this entire quantity, and then leave this delta t squared out here. And then finally, I would take the square roots here of the entire equation, giving me square root of delta x over delta t quantity squared plus delta y over delta t quantity squared, and then times delta t out here by itself. You can see that even in the picture, right, this is not a very good approximation to, by this I mean this length is not a very good approximation to the arc change in arc length here between the 2 points. But you can convince yourself that as x gets smaller and smaller and smaller and smaller, I get a better and better and better approximation. So in the limit as delta t goes to 0, right? This is said another way. If I do not wait before drawing, I don't wait very long before drawing these 2 points, then I am going to get these infinitesimal changes. Infinitesimal change in the arc length is dx over dt squared plus dy dt squared times dt. So this is a great formula to remember and to make sure you understand, because it tells you how the arc length changes infinitesimally based on an infinitesimal change in t when you have a parametrized curve of the form x of t, y of t. And you might remember now how this goes and relates back to calculus 1, where you say, oh, so the length of arc length of the curve is equal to the integral of ds over the entire curve. We're viewing it there in the notation of the line integral above, where the function f is 1. And we can write this now with our handy-dandy ds that we just derived here in terms of the parameter t as follows. So we put a dt there. And then we're integrating. Remember we had said t equals a is where we start the curve, and t equals b is where we end the curve. So we're integrating from a to b. So this is the formula that you probably saw in calculus 2 for the arc length of a curve. You might have seen it written a little differently. It might jog your memory more to remember it as 1 plus the derivative squared dx. You might have done that. This is a way to parametrize a specific parametrization when you're dealing with a curve of the form y equals f of x. If you are dealing with that, then you can parametrize your curve as x comma f of x. And if you parametrize it that way, then x is like your t, and this is your f of t. So dx dt is 1, hence the 1 there. And dy dt becomes dy dx, that's your f prime, hence the f prime there. Okay, so now we have done all of the connecting to single variable calculus, arc length. And we have also gotten this expression, which is going to recur throughout these lesson notes. Excuse me. And we have also seen that the arc length that you know and studied in single variable calculus is a line integral with a very special f function, f equals 1. All that being said, we finally arrive at our theorem. Suppose f is continuous on a smooth curve C. By smooth in this lesson, we mean a curve like the ones I've drawn, not something with jagged edges. We'll talk about that in a minute. Or not something with some very, very crazy oscillations. These are not smooth curves. And continuing the theorem, if C is parametrized as x of t, y of t, where t is in some interval, then the line integral equals exactly what we just basically talked about. So we replace ds here with this quantity. So that comes again from this formula. And then, well, we said x and y were parametrized by t. So we replace x with x of t and y with y of t. So, excuse me. Let me go now and show you an example of how this works. So here's an example where C is the upper half of the unit circle x squared plus y squared equals 1. And then I want to evaluate this line integral. So first thing I'm going to do is I'm going to plot my curve. So that's my upper half of the unit circle. And then I have to parametrize it. Why? Because remember, we just talked about how this is equal to the integral of 2 plus, I'm going to have to find, what the x and y parameters are, times the square root of, stuff squared here, dt, where the things that belong here are the derivatives of x and y with respect to the parameter t. So I want to parameterize a unit circle. You probably have seen this in previous videos already. The easiest way to parameterize the unit circle is to choose x equals cosine of t, and then y equals sine of t. We'll see a little later that it doesn't matter whether you start here and go that way, or whether you start here and go this way in terms of sweeping out this unit circle. So I'm going to choose the first one. I'm going to choose my range for t so that this is t equals 0, and that this is my last value, and we'll see that that's t equals pi. Okay, so if I'm here in the initial starts, I'm at the point 1 comma 0. So cosine of 0 is 1 and sine of 0 is 0. So indeed, that tells me that I can choose this to be t equals 0. And then I want to get to this last point over here on the upper half of the unit circle. I know excuse me, that cosine of pi is -1 and sine of pi is 0. So there again, this tells me that I can get there with t equals, after time, t equals pi. So this is -1 comma 0 at t equals pi. All right, so I have my parameterization then up here. And t goes from 0 to pi. And again, that is parameterizing this upper half circle with a certain orientation, a counterclockwise orientation. Okay, so now I have obtained my x and my y. So everywhere I see an x and a y, I'm going to put them in there. So this gives me cosine squared t times sine of t. And then over here goes the derivative of x. Derivative of cosine is negative sine t. And then over here goes my derivative of y. Derivative of sine t is cosine t. Great, and now my bounds for t I had found to be 0 to pi, so I put that in there. And there we go. I just now have a single variable integral, right? Everything in here depends on t. So I'm going to simplify a little bit, but leave you to work out the details so that we can get to the new skills in this lesson. Notice that this is effectively sine squared plus cosine squared, which equals 1. So this entire square root goes away. And I am left just integrating this integral, this integrand. And how would I do this? Well, I can split it up, right? The 2, I'll just talk through how to do this. The 2 becomes 2t, and then evaluate it from 0 to pi. That's going to give me 2 pi. Over here, what can I do? Well, I can use a u substitution. I can let u be cosine. The derivative is negative sine, so I'll have to integrate to negative cosine cubed t over 3. And then I'll evaluate from 0 to pi, and you can verify that that will give me 2/3. Okay, last thing I want to say, right? I mentioned that this is a particular orientation of the circle, going from here to there. And I also mentioned that we could have gone the opposite direction. We could have started here and gone over there. With the same parameterization, we could have achieved that by not starting with t equals 0, but starting with t equals pi and going to t equals 0. So what that would have done is essentially changed swapped these bounds. So the new integral would have been integral from pi to 0 of all of this stuff. Okay. One of the properties that you can verify, and I'll write it down here in more abstract notation, is that if I find the integral, the line integral of f of y dy with respect to arc length over the curve C, it's the same as if I took the opposite orientation, which I'm going to denote here as usual, as it's denoted commonly with a minus c. So if I took the opposite orientation for the curve C, if I parametrized it in the opposite direction, one of the properties of line integrals that you can show is that these two line integrals are actually exactly the same. So you can keep working this out and you can see that you will get exactly the same answer here. We don't have to worry about that when we're parametrizing with respect to arc length. Okay, so then let's talk about this next portion. So what if I am not working with a smooth curve, but what if this curve that I'm working with, it's not a smooth curve like this, but what if I can draw it here, and then maybe I can draw it there, and then maybe I can draw it there. In other words, what if it is smooth in pieces? Well, we call such curves piecewise smooth curves, the unions of finite number of successive smooth curves. And if we again suppose that f is continuous on C, meaning in particular all of these pieces, then we are going to define the line integral over such piecewise smooth curves as just the sum of the line integrals over all of these subcurves, if you will. So that allows us to extend what we've been doing with line integrals to treat examples where the curves can be basically connections of or unions of two other curves. So here's an example that I want to work through to help you visualize that. So suppose that I look at the curve C, which is traced out as follows. It's first the parabola y equals x squared from 0 to 1. So let's draw that. Here's 0, 0. Here's 1, 1. And then there's the first part of the curve, and traced out in this orientation. And then followed by the vertical line segment traced from 1, 1 to 1, 2. So 1, 1 to 1, 2. So here's the other part of the curve. I'll put this one in black. Excuse me. So this entire curve is my curve C in this problem, and it's made up of these two curves. I want to evaluate this line integral. So how would I do that? Well, based off of our definition above, I would say this equals the line integral over the first curve, 2x ds, plus line integral over the second curve of 2x ds. And, again, that comes from this definition here. And therefore, I am reducing the problem to evaluating two different line integrals and then just adding up the results. So in the first line integral, then I'm going to look at this first curve over here on the left, the blue curve. This is the parabola. I am going to have to parametrize this curve. And, we could leave it with a parametrization in terms of x, but just to get you used to continuing to use t, let's parametrize it with x equals t and y equals t squared. Notice, by the way, that this indeed gives us y equals x squared, which is the original parabola we were working with. Great, so we're going to parameterize it this way. And then x here goes from 0 to 1, so that, because x equals t, is my bounds for t. T goes from 0 to 1. So I can therefore write down my first integral. This is integral from 0 to 1 of 2 times x, which is t, and then ds. So this is the square root dt, and then a sum of squares of the derivatives. If I look here, dx dt is 1. If I look here, dy dt is 2t. Great. And then I start just writing this out a little bit more. 0 to 1 of 2t, square root of 1 plus 4t squared dt. And I'll stop there because now, again, we're back to single variable calculus, and we have an integral which we could evaluate using integration techniques you learned in that course. So I'm going to move on then to this second part of the integral. So now I'm looking on the left-hand side and I'm looking at this portion of the curve. And I'd like to parameterize that. Well, this is a special curve because it's actually a line segment, which always has x equals 1. So that's an easy way to parameterize that. And then y, I can express y as t. And then because y goes from 1 to 2, I can say that t ranges from 1 to 2. Okay, so that's my parameterization. So I'm going to write out this integral, the integral from 1 to 2 of 2x, which is just 1, multiplied by our usual square roots of the dx dt squared plus the dy dt squared. So looking over here, dx dt, that's 0. Looking over here, dy dt, that's 1. So this one is particularly simple. So I get integral from 1 to 2 of 2. This is just square root of 1, which is 1, 2 dt. Great. So I have now reduced my line integral to a sum of two integrals that are integrals I can do in single variable, using single variable calculus techniques. Certainly this one yields 2t evaluated from 1 to 2, which gives us 4. It gives us, let's see, not quite 4, it's 4 minus 2, so that gives us 2. And then this one, just to talk through what we could do here to evaluate it, notice that if I let u be this, then the derivative du is 8t, which 8t dt, which contains 2t times 4. So in other words, I could do this integral as a u substitution. So again, that's another technique that you've learned, so I'll leave you to do that part. And that's it for this module. In the next module, we are going to talk about scalar line integrals over planar curves with respect to x and or y. So things are going to change. We're going to move away from using ds as the parameter that we use in our line integral, and instead we're going to go back to using the more familiar dx or dy, and we'll see what changes then. Okay, so I'll see you in that next video.